Okay, so let's move on to 1.3, which is probability. And we're going to start by talking about discrete probability, and then from there we can generalize it with continuous probability or continuous variables. So let's just imagine you have the following arrangement of people in a room. You have one person. Oops, that's not what I want. You have one person that's 14. You have one person that's 15. You have 3 people that are 16. You have 2 people that are 22. You have 2 people that are 24. And you have 5 people that are 25 in some sort of room or building or something. And the question is, what can we do with this information, this data? So to begin with, we're going to use this notation, n sub j, and that represents the number of people of some age j. So for example, n sub 14 is 1, n sub 15 is 1. I don't know why I said sub 15. N 16 is 3, n 22 is 2, n 24 is also 2, and n 25 is 5. So this tells you for whatever age how many people there are. Okay? N is going to be the number of people in the room. That's not how you spell the word people. Okay. So obviously, if you wanted to know how many people they were in the room, you could just add all the numbers here up. So n is going to be a sum over however many j's we have, n sub j. So you add up how many people are 14, 15, 16, 22, 24, 25, and you'll get the total number of people in the room. So that's pretty straightforward. Okay? Now, if we were to pick out of this data point at complete random, what is the probability that that person's age is, say, 15? Well, if you count these up, in this case, there's 14 people, and there's only one person that's 15. So out of the 14 people, there's only one chance that you'll get someone that's age 15. So P, the probability that you find someone at 15, is 1 over 14. The probability you find someone age 25, well, there's 5 people that are 25, so that would be 5 over 14. And you could do that with all the different numbers. So the probability that you find somebody age j is the number of people that are that age divided by the total number of people in the room. Okay? And from this, we can get another property, which is if you sum over all the ages, the different probabilities, they should equal 1. In other words, if you pick somebody at random, they're going to have an age. Okay. The next question is, what is the most probable age? So let's see. Most probable age. Well, it's just going to be the age group with the most amount of people in it. So in this case, 25, right? Okay. What about the median age? So what you can do is kind of set this up. This is how I like to do it. 14, 15, 16, 16, 16. So I'm laying all the people out. 22, 22, 24, 24, and then a whole bunch of people that are 25. I think I got that many, right? To find the median, we just kind of go down the line like this. That's how I remember doing it in, like, I don't know, 5th grade or something like that. And then 22 plus 24 over 2. Let's see, that is 23, of course. So the median age is 23. Okay? Even though no one here is age 23. So just because there's no one there of that age doesn't mean it can't be the median. And likewise, there's an average or mean age, which can be found by adding all the different people up. And then we will divide by the total number of people, 14. And when you do that, if you do this math, you get 21. So the average age in this room is 21. But again, if we look at our data, there's no one here age 21. So that's interesting. We're going to talk about that in a second. But first off, I want to talk about average because that is something we use a lot in quantum mechanics. So the average is, I'm just generalizing essentially what I did up above. It's the age times the number of people of that age divided by the total number n. Now if you go up, you'll notice n sub j over n is just the probability. So this summation can be simplified a little bit over all j to j times the probability of j. Okay. So in quantum mechanics, we usually don't use the word average. We use expectation value. But it's just an average. Now, the problem is when you call something an expectation value, this is a big misconception that you see a lot early on in quantum mechanics, is when you call something expectation value, it's pretty natural for the students to think that whatever this expectation value is that I calculated, that's the expectation value that I expect to get. But that's not what the expectation value is. The most probable age is what you would expect to get. The expectation value, or the average, is just that. It's an average. It's not necessarily something you're going to get. It might not even be anything in your data set like it was here. So that's important to keep in mind. Another thing that's important is the average of squares of ages. So we'll just say average of the squares. Okay. And it essentially works just like you would think it would. If you square the ages, now your sum, instead of being j, will just be j squared over all j. And it doesn't have to be squared even. If we wanted to, if you want to be general, any function of j any average of a function of j can be written as the sum over all j of fj times the probability of getting j. Okay? Now I do want to talk about this because usually in quantum mechanics we're interested in the average squared and the square of the average. And I just want to show you that this is not the same as this. Sometimes that trips students up. They're not necessarily equal. So if we take a very easy example, let's say you have two people. One is age 1 and one is age 3. Calculate the expectation values here. Okay, so if we wanted to find squared, that would be the sum over all j of j squared times the probability of j. So that would be 1 squared, which is 1, times the probability. It's a half, there's only 2, plus 3 times a half. So this is 1/2 plus 3 halves. I did not square the 3, so that should be a 9. That's okay, no big deal. 1/2 plus 9 halves is 10 halves, so that's obviously 5. But now let's just get the expectation value of j, which is what I was calculating before I realized what I was doing. So that'll be just 1/2 plus 3 halves, which is 4 halves, which is 2. And then after I calculate the expectation value, if I square that, that's 4. So 5 is not equal to 4. So at least in general, the expectation value of our square is not equal to the square of our expectation value. Okay, and now what I want to talk about are these two graphs here that you can find in the textbook. Because if you were to go and calculate the different values like the mean, the average, the median, the number of data points, you'll find that they're all equal. The averages, it's all equal. But clearly these graphs are a little bit different. In the first graph, there's this very sharp peak at 5. And on the graph on the right, it's not as pronounced. So that leads to the motivation of defining the spread of the distribution. And that's kind of what we're going to get into now. Now, one way to do that would be to take all the different data points and see how far away they are from the average, which seems like a pretty good way to calculate the spread, how far away you are from the average. But if we take the average of this, so we average how far everything is from the average, well, let's calculate that. That'll be the sum over j minus expectation value of j times the probability of j. And we can actually break that into two different summations. So we have j times the probability of j. Did not mean to put that up there. Minus the expectation value of j, that's not going to change, so that can come outside of our summation. Times the probability of j. Okay? Well, this is just 1, and this is just the expectation value of j. So you get the expectation value of j minus the expectation value of j, which is obviously 0. So that doesn't quite work. Instead, what we do is we define this sigma squared, which will be our variance, as the average of delta j squared. Okay? So let's go through and let's calculate this. So sigma squared then is the summation of delta j squared times the probability of j, since it's an expectation value. And we have our definition of delta j. So this is equal to the sum of j minus the expectation value of j all squared times the probability of j. We can expand that term there to get j squared minus 2j times the expectation value of j plus the expectation value of j squared times the probability of j. Now we can write this into three sums. So we have the summation of j squared pj minus 2 times the expectation value of squared times the summation of j pj. I think I say p sub j a lot. I don't know why. It's not a subscript. But hopefully everything's still clear. Again, expectation value is a constant, so that can come out. Expectation value of j squared times the summation of pj. Again, this is 1, right? And this is going to be just the expectation value of j, and this is the expectation value of j squared. So we get j squared, its expectation value, minus 2j squared plus j squared, which is just the expectation value of j squared minus the expectation value of j all squared. And that's our sigma squared. And of course sigma then is just the square root of this. Which is often called our standard deviation. Okay? So that tells us how spread out our distribution is. And if we want continuous functions, so here we had discrete data, you had 1, 2, 3, data like that. But if you had a continuous line of data, we can extend this, what we learned here, to continuous data. Okay? So first off, there is this rho sub x, d sub x, and all that this is the probability that of finding, or we'll say finding your data between x and x plus dx. So this is what's known as your probability density. Probability density. And the probability of finding, say, a particle between A and B is just the integral between A to B of rho of x dx. So a lot of our sums are now going to turn into integrals. And just like before, the same rules of probability apply. If you integrate, just like if you summed over all your data, if you integrated over all your data, you should get 1. And if you want an expectation value, say of x, you multiply your x by this probability density function. And in fact, if you want the expectation value of anything, it's just the integral over that range whatever our range could be, or from negative infinity to infinity, sometimes you can make it lower, is just f of x, rho of x, dx. And our standard deviation, or variance, is going to be the expectation value of x squared minus the expectation value of x squared. So a lot of what we found with our discrete variables can be applied to our continuous variables. In the next video, we'll talk about normalization, which is another important topic in quantum mechanics. If you found this video helpful at all, please like and subscribe, and I'll post more.